Okay, so I remind you that we had started yesterday on our en route to trying to prove the spectral theorem for self-adjoint operators on Hilbert space. So I started by showing that for any normal operator, every point in the spectrum is an approximate eigenvalue. So let me prove a couple of other things, some of which are quite standard, which you may be familiar with. So I retain the same numbering, so this is number 2. So this for a general x and b of h. Place x is inverted. You all know this theorem, right? The binomial theorem. Not binomial. Whose series? Neumann series. Right? So 1 over 1 minus x equal to summation x to the n. So the proof, one just has to show that summation 0 to infinity of x to the n is the inverse. So this by definition, of course, you want to prove that limit n, too many n's, m you want to show this converges. You want to show this converges and is the inverse. This limit exists by y. If you have a series in a Banach algebra,
absolutely convergent economic is any absolutely convergent series converges.
So if a series is norm-convergent, then it's automatically convergent. And because norm x is less than 1, the series is convergent, so this is going to be a convergent series. And one verifies that if you call this as Sn, the mth partial sum, and you just see what x times Sm is. It's going to shift everything from 1 to m plus 1. Right? So, Oh, you're right. Want to find the inverse of x, so you think of it as 1 over 1 minus x. So you want to show that this is a series that converges by this hypothesis. Consequently, you want to prove this converges. Now, if you take 1 minus x times Sm, so what is the difference? It just slides everything. Sm is from 1 up to 1 minus x power m. If you multiply by 1 minus 6, then you start from the first term. So if you compare these two, see this, so 1 minus x Sm minus Sm. If you see, then you'll get just this minus this, right? So 1 minus x to the m plus 1. Minus 1, right? Is that correct? So which means that this converges to minus 1. That means Sm minus xsm minus Sm converges to minus 1. That is just that xsm converges to 1. Similarly, Smx converges to 1. See, you must be careful that you are working with a non-commutative algebra. B of h is not commutative. Just because the left inverse has a left inverse doesn't mean it must be invertible. So you must check both the both the left inverse and the right inverse before you can conclude it's invertible. But here you can verify by exactly the same rules that this limit, we call it if you call the limit as z, therefore z equals x and s. Right? So this is just straightforward computation. So, so this is the familiar Neumann series, which tells you that elements close to 1 must be invertible. Okay. 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 I want to say next that, see, if we define actually let me write down a corollary here itself before I get to this. So from this, one has a corollary that mod lambda bigger than norm x implies x minus lambda invertible. Because you can write this as lambda into minus lambda into 1 minus x over lambda. And by what you've seen before, norm of 1 minus x over lambda is smaller than 1. This lambda is after all a non-zero constant, so the whole thing will be invertible. Okay, so what this has shown is that the entire complement of the disk of radius norm x about 0 is contained in the so-called resolvent of x. That is the complement of the spectrum. So the conclusion that I wanted to draw was therefore the spectrum of x is bounded actually I should have also in fact, so that already says the spectrum is contained in the ball of radius norm x, and so if one defines let me call R of x, this is so-called spectral radius of x. Which is the sup over mod lambda and spectrum of x. Then you take the smallest disk containing the spectrum and you look at the radius. Smallest disk center 0 which contains the spectrum, and take the radius, that is called the so-called spectral radius of x. And so they said that the spectral radius is bounded then. So I guess I should have said this before, so let me actually let me say it's not just bounded, but in fact it is compact. Yes, that means I must show that it is closed. And I don't know how many of you have seen this. In fact, this Neumann series itself can be used to show that the inverse mapping is continuous. See, this says that if x is close to 1, x is invertible, and one can even see that see what is norm, what is x inverse? X inverse was the sum of this series. That series, the series starting with it is 1 plus the power series 1 minus x power n. So the series says that x inverse minus 1 itself is the series in 1 minus x. Right? So if 1 minus x is small enough, it will follow that x inverse will be close to 1. Or in other words, that the inverse mapping is continuous at 1. That means if you get close to 1, you'll be invertible and the inverse will also be close to 1. If you multiply that whole thing by an invertible element, I'm saying too many things, maybe see what I'm saying is that what we showed was that see 2 implies that norm x inverse minus 1 goes to 0 as norm x minus 1 goes to 0. That is the observation that I made. As x approaches 1, x inverse approaches 1. I guess there is a more natural way to say it. There is limit as x approaches 1 of x inverse equals 1. That's what I'm saying. Now the point is that see B of H is an example of Banach algebra. That is it has the product is related to the norm by being submultiplicative. Norm AB less than or equal to norm A, norm B. What that means is that if A is invertible, then x going to Ax is a homeomorphism of B of H onto itself. See, all this is true in any Banach algebra. I'm only using the fact that it's a Banach algebra. Right? Because submultiplicativity says that multiplication by A is a continuous mapping, continuous operator. And clearly it's, if I call this LA, left multiplication by A, it is clear that LA inverse is LA inverse. And so it has an inverse which is also continuous. That is why there is a homeomorphism. So okay, so what did this observation say? See, star says that the mapping, inverse mapping, x going to x inverse, is continuous at 1. Okay. So if you compose this mapping, this inversion mapping with this LA, you will find that is that clear? So by composing with LA, so LA, the homeomorphism implies that this is continuous at A. Right? If AN goes to A, then you want to say AN inverse goes to A inverse. AN goes to A means A and A inverse converges to 1. And that means for large n, A and A inverse will be invertible. But A inverse is already invertible, that means that AN must also be invertible. Right? So just a little bit of Jagdeep will give you this fact. And hence, this inverse mapping is continuous. So to finish the proof of what I am saying here, if you look at B of H or any Banach algebra, so what? What do I want? Yeah, you look at the mapping from C to B of H, where lambda goes to x minus lambda. This is lambda. For a fixed x in B of H. Then this is clearly continuous as a mapping from C into B of H. So this is continuous, and from B of H to itself, the inverse mapping is continuous. Consequently, the composite mapping is also continuous. Lambda going to x minus lambda inverse is continuous. And I guess I didn't say that. I'm doing everything upside down. Huh? Question? Somebody said something. Third occasion. No? No, I want to say that the invertible, let me call that let me write GL away, away. That is all those things which are invertible. All those x. X is invertible. So the noise I am trying to make is that this is an open set. It's open and x going to x inverse is a homeomorphism. On the GN to itself. So this is what I said earlier about 1 should be used over here. See, what we first proved was that 1 was an interior point of GL and that the inversion is continuous at 1. And then using all these left multiplication maps, pushing that 1 around, we'll find that every invertible element is an interior point of GL and that the inverse mapping is continuous there. So that is just what I'm saying here. And consequently, so at the end of the long story, if you look at C minus spectrum of x, which is all the lambdas such that x minus lambda is in GL, is open. This is usually called the resolvent of x, denoted by rho of x. And so what they say is that therefore sigma x is closed. We've already seen it bounded, so the spectrum is compact. Okay, so let's go to the next item on the agenda. This is so-called spectral mapping. Okay. Or at least a special case. So what I want to say is the following thing. I take a polynomial P of t equals summation 0 to n from Cj to the j. Or let's write P of z. Think of z, the variable as complex or real as the case may be. So take such a polynomial. So now what one wants to say is that so given such a polynomial, one may also take P of x, where x is an operator, by just substituting x for z. Then P of x is an operator. Right? So the theorem says, how do I find the spectrum of P of x? And the answer is that this is so the right hand side I'm thinking of P as the mapping of the complex plane into itself. And I'm looking at the image of the spectrum under this mapping. And on the left hand side I'm just taking the spectrum of this polynomial of x. Okay, so let's start. So let's fix the proof. Let's fix lambda in. Let's see. I want to see when lambda belongs to the spectrum of P of x. Right? To do that, I look at, consider P of z minus lambda. This is a complex polynomial, and by the fundamental theorem of algebra, that will split into linear factors. So you can write this as product z minus mu I. See, you can see I've just come back from America. I said you can see I've just come back from the US. Z minus mu. Yeah, of course the mu i's need not be distinct. They may coalesce. Okay, so I want to observe, so I want to make a certain claim, assertion. I want to say if x1, xn be a weight, all commute, all commute. There is. So I'm being careful to put on the hypothesis up front, because the statement I'm going to make is false in a non-commutative algebra. So this is a statement about a commutative algebra. If you take any commutative algebra, then this says you take any n elements there, then a product can be invertible only if everything is invertible. This is something specifically for. So if you looked at studied Hilbert space operators before, then the first thing, example of infinite dimensionality of Hilbert space is conveyed to you through the example of the so-called unilateral shift. The shift operator will send the basis En to En plus 1. So, if you call that operator, for example, if S is the right shift, on L2. Right, so it will send the sequence to and see in Hilbert space one has an adjoint operator. So one can see that the adjoint operator is the left shift. And this is the guy who sends it will kill the first coordinate. And then send everything, send the sequence to the left. So one can see that in fact S star S is the identity operator. You always write 1 for the identity operator. So S star S means you first you first shift to the right, then shift to the left, then you get it's like haven't done nothing. But if you first shift to the left and then shift to the right, then you will find that but SS star is not equal to 1. Because SS star will have send any vector sequence to the sequence with 0 in the beginning. And it will, no, I said that wrong. It will send, no, it will send, it will kill the E1. I'm saying SS star will kill the basis vector E0. I'm not saying that it will have the first coordinate as 0, the image. SS star of anything is just going to be, oh yeah, it is, yeah, 0 and then all the others. Alpha 1, alpha 2 only. So here is an example. See, S and S star do not commute. So, and neither of them is invertible. But the product is 1. You can't be more invertible than that. So this is a purely commutative algebra theorem. Okay, the proof is more or less elementary, because if you have a bunch of invertible things, clearly the product is going to be invertible. Its inverse is going to be the product of the inverse in the opposite order. Conversely, if the product was invertible and if they commuted, then so how do we say this properly? Or since we're talking about operators, let me talk operators. I want to show that every xi is invertible. I want to assume the product is invertible and show that every xi is invertible. That means that every xi is 1 to 1 and onto. So I want to say that xi is 1 to 1. By commutativity, I might as well assume that I is 1. I is n. If we take x1, x2, xn, I just rearrange them so that xi comes to the right extreme. So if xi killed anything, then one should kill that. That invertible operator should kill that thing. Right? So no xi can afford to have kernel. And similarly, if some xi, I want to say that every xi is onto. So again I rearrange them, but now I put xi up front. So I want to say that if x1, x2, xn is invertible, then x1 must be onto. If the entire product is onto, then of course the last operator should be onto. Okay, there will be more clever algebraic proofs of this. But anyway, since we're talking operators, let me just say that everything must be 1 to 1 and onto. Okay, so now we're getting back to the spectral mapping theorem. So what is see, so started by saying let Pz minus lambda be product Z minus mu I. So it follows that Px minus lambda will also be x minus mu 1, x minus mu n. But now all the x minus mu i's commute. So I can use the lemma that we just proved and conclude that therefore what does it mean to say lambda is not belongs to the spectrum of Px? This means that LHS is not invertible. But we already saw that such a commuting product can fail to be invertible precisely when one of those factors is not invertible. Right? Because if all of them were invertible, then the product would be. So that means there exists an I such that mu I is in spectrum of X. That is the same as saying that lambda is in P of spectrum of X. If you look at this equation, lambda can be P of somebody only if that somebody is one of the mu i's. Right? So you've shown that if lambda is in this spectrum, precisely when it is in the image of under P of the spectrum of X. So now, so a couple more of these silly things we'll do, and then we'll get to something interesting. I want to say X in GL implies spectrum of X inverse equal to that is the same as the spectral mapping theorem, except we are applying it to the reciprocal function. I'm taking P of Z equals 1 over Z. Actually, the spectral mapping theorem is true for any analytic function which is defined on the spectrum of P. So, if it is in GL, that means 0 is not in the spectrum. So, 1 over Z is going to be an analytic function in a neighborhood of spectrum of X. Okay. So this is obvious, isn't it? What do they explain lambda? The invertible what is this? First, lambda can't be 0 because we assume that X is invertible. If lambda is not 0, and I can pull out the lambda factor, lambda into minus lambda times 1 minus x over lambda is invertible. I'm trying, let me put it straight for x inverse. Therefore, lambda is in spec x inverse. And now, if I change it for x inverse, then what do we get? 1 minus 1 over lambda times x inverse. That is the inverse of lambda x. Why am I playing the one? If x minus lambda is invertible, x inverse minus 1 over lambda I will get. So no, I will write the same thing as lambda, I will write the lambda x inverse. See what is this? This is equal to x minus lambda x inverse, which is x times 1 minus lambda x inverse. So, and these are commuting things, so it shouldn't be so hard. Why am I making such a mess?
Sir, this concern, as you told, this is true for analytic function also.
No, let me not use things which I haven't proved.
So x lambda is in spec x means x minus lambda is not invertible.
Okay.
So you multiply by x inverse that comes.
Okay, so
Write x inverse minus lambda inverse.
so you're saying lambda in spec of x inverse.
So x minus lambda not invertible.
Spec x inverse or x?
No, x minus lambda is in spec x. So x
Okay.
minus not invertible. So we can multiply with x inverse. Yeah, and lambda inverse.
Or you write x inverse minus lambda inverse is not inverse. X in minus x inverse. X
This
minus
you can write as a product of things like
Yeah,
that,
product
right?
of x minus lambda and x inverse lambda is.
For to get x, I must
minus
have.
x inverse minus x inverse x minus lambda
Sorry,
lambda
what?
inverse.
So what is the factor of this?
X inverse, that's x inverse,
X inverse
x minus lambda,
lambda.
minus lambda, 2 minus lambda.
and all these fellows commute. Everything commutes, so if they are not invertible, then it just means one of these should be not invertible.
But x inverse lambda. So
Oh, x inverse and lambda inverse are invertible.
no, x minus lambda is not invertible. So x inverse minus lambda inverse is also not.
It's a broad, that's it. And not invertible. That means, so lambda inverse not in spectral equivalence. Okay. Couple more, one more such thing, which is, I want to say that the spectrum of X star that this is true not just for analytic, even for the conjugate function. It's not analytic, but for that also it maps the spectrum properly. Right? This will be let me not try and prove this is obvious, right?
Same tricks.
Huh? Yeah, huh?
So lambda is to take the x star minus
X star minus lambda bar.
X star minus lambda power you write as
x minus lambda.
minus lambda bar
So there is x minus lambda whole star. That's it.
X minus lambda. X minus lambda.
there. And the star mapping reverses by an anti-algebra isomorphism, anti-isomorphism. So, and which fixes one. So clearly it maps invertible things to invertible things. So in particular, corollary is that A is alpha joint implies the spectrum of A is contained in R. And left invariant by the conjugation map. And now here is the this clever little trick by so this item is where we would use the fact that A is self-adjoint crucially. That is in a proof of the spectral theorem for self-adjoint. This thing is going to use the self-adjoint as a way very crucially. So if you can modify this to work for normal operators, then we'll have a correspondingly simple proof of the spectral theorem for normal operators. Okay. So it says that A self-adjoint implies norm A equal to the spectral radius again. So this means the spectrum, no, I shouldn't have said, yeah, this is positive. So, okay, it's clear what it says. Okay, so this requires some amount of cleverness, so I just have to copy. This is, I don't know where Hermes picked up this trick. So it says, he got applied for proof. Let lambda in R. Actually, he going to choose lambda to be equal to norm A. No, corollary is proved because of this. The spectrum of X star is the image of spectrum X under the conjugate mapping. So if X is self-adjoint, so it says the spectrum of A is spectrum of A conjugate. Oh. So it can be why didn't I? Okay. Huh?
Sigma A equals to sigma A.
No.
That doesn't mean
No, let me put it this way. Okay, so let me come back to this. So because we've proved the thing that even for normal things, that anything in the spectrum is an approximate eigenvalue. Right? So if lambda is in the spectrum of A, there exists Xn such that norm of Axn minus Xn lambda Xn converges to 0. Take inner product with Xn. That means Axn doesn't call as In. So A is In minus lambda, these are unit vectors. And the way self-adjoint, all these things are real. Yeah. So because of that fact that all points in the spectrum are approximate eigenvalues, we find that every such lambda must in fact be in the real line. Okay. So now let me get to it. So getting excited by getting to the heart of the proof. Okay, what do I want to prove? The norm A for the spectral radius array. So proof, so put, let us write lambda equal to norm A. So what I will say is that, so we prove that plus or minus lambda belongs to spectrum of A. Then by definition of spectral radius, so it is we will take modulus of that point in the spectrum, and so we will find that. Is it clear? See, the spectrum of A is a subset of the real line. So let's think of this as an interval if you want. A bit contains 0. And maybe it looks like this also. So what this says, see, if the, suppose the spectrum is the interval from -3 to 1 or something like that. So the spectral radius is going to be 3. And what we are saying is, so
minus 12 is there in the learning. A is positive.
huh?
A is positive.
No, who said A is positive?
Which is self-adjoint.
It is self-adjoint, right?
It's positive and self-adjoint.
No, we are not assuming positivity. Okay.
I think once that was proved, limit of non-equal to 1 by n equals to r.
Sorry?
R of A equals to limit of norm of A n by 1 by n. Then
No, that is yeah, okay, sorry. See, suppose the norm of A is 3. If norm A is 3, then you know that the spectrum, if you know that lambda is 3, then you know that the spectrum is, you know it's real, so that will say it is contained in -3 to 3. Because the spectral radius is less than or equal to the norm. So the spectrum is contained inside a disk of radius, the norm, and hence also the spectral radius. But what I am saying is that if either -3 or 3 is actually going to be in the spectrum, I am saying. So that will say that the spectral radius is at least
Not
3.
one of them, but not, I mean, it may not, at a time both of them may not.
Yeah, may not, that's what I am saying, the spectrum could have been just -3, 1. I'm just saying, I'm not saying both of them, either one of, either lambda or minus lambda is in the spectrum is what we do. Is it clear that once I have proved that, it will prove that norm A is the spectral radius of A? Okay. Okay, I claim that assertion the norm A squared is in spectrum of A squared. See, by spectral mapping theorem, it is enough to prove this. See, the spectrum of A squared is going to be the image of spectrum A under the squaring map. So if I prove that the square of norm A is in the spectrum of A squared, it will prove that either plus or minus norm A must be in the spectrum. Okay. So this is what we have to show. Okay, so now observe for any x that norm A squared x minus lambda squared x the whole square. So I'm going to do a little magic. This is
X is an operator.
huh?
X is an operator.
Sorry, right. So compute this, so this is inner product of this guy with itself. Okay, now expand, so you'll get norm A squared J squared and the other the n term will give you plus lambda to the 4 norm J squared and what are the cross terms? Minus you have A squared J, lambda squared J. Lambda is real, right? So I can take the lambda squared out. A squared J J is going to be norm AJ squared. See, this cross term is going to give you this much. And the other thing is also going to give you the same thing. Right?
Norm of Giants law.
Okay, let's assume the norm size is 1. Take a unit vector and then so you have A squared J, lambda squared J. That will give you lambda squared A J J. Now this time use any norm J equal to 1. So why did you say norm J is 1? Okay. So we've done this little computation which says norm of A squared J minus lambda squared J the whole squared is this quantity. Okay. Now he says by definition of norm it is the soup of unit vectors or something. So there exist unit vectors psi n such that norm of A psi n converges to norm A, which is our number. Now apply the star to psi n's. What you find is that norm A squared psi n and lambda squared psi n squared equal to norm of A squared psi n squared then lambda 4 minus twice lambda squared norm is A squared psi n squared. Okay. Now this is the magic. Norm A squared psi n, I can pull out one A. Norm A squared psi n is bounded by norm A and norm A psi n. So that's an equal to, and there is square of the whole thing. So norm A squared and norm A psi n squared. So lambda to the 4 minus twice lambda squared norm A psi n squared. Now in the limit what happens here? A psi n is converging to lambda. Right? So this converges to lambda squared. This also lambda squared. Huh?
A psi n converges to norm A psi n converges to norm A square.
No. Norm A psi n converges to norm A,
Norm A, oh I see, that's lambda.
which is lambda. So norm A psi n squared converges to lambda squared, here another lambda squared. So this gives you lambda to the 4, and this is also lambda squared. So lambda to the 4 plus lambda to the 4 minus twice lambda to the 4. So the right hand side goes 0 as n goes to infinity. And so the conclusion is that A squared psi n minus lambda squared psi n converges to 0. The psi n are unit vectors. That means lambda squared is an approximate eigenvector of eigenvalue of A squared. So this shows that lambda squared is this spectrum of A squared. This deserves some pondering over it. There's some really clever little magic. But when I got this beautiful theorem, this is the essence of the spectral theorem actually, this identity. In fact, once you get, because you have the spectral mapping theorem, one can get the stronger theorem, statement that if P is the real polynomial, that means a real polynomial with real coefficients. That means that P of A is going to be self-adjoint. Okay? Which is say P of spectral radius, no, they can be negative sign. So spectral radius of P of A is so what is this by definition? In the soup of the modulus of things here. What are the lambdas in P of the spectrum of P of A? Right? Which I can write as soup of spectrum of P of A is the same as P of spectrum A. So we can write this as mod P mu in spectrum A. Right? Which is the soup norm of P on the spectrum of A. So let me introduce the notation norm P subspectrum A to denote this quantity. So I have a function defined on something, on a set, I write norm F sub x to be soup norm of F on X. So this says that the operator norm of P of A is the same as the soup norm of P on the spectrum of A. And this is really the essence of the spectral theorem. And once from here, I think I should probably stop here, because from here is when we start applying this, and this will tell us how to identify what A looks like in terms of the spectrum of A.